We will wait for a couple of more minutes, then we can start. So am I audible?
Yes, sir.
Okay, thanks. Fine. So let's start. So welcome to this fourth interaction session of the course Rings and Fields. So in last interaction session, we are discussing this practice assignment 5. In the first problem we discussed, and now we will discuss the second problem of that practice assignment and then sixth practice assignment. So let's start. So is there any doubt in the first problem? I hope no. Okay, let's start. Second. Let's write this as a first question. So let R be a principal ideal domain. So what is a principal ideal domain? Someone can reply. What is a principal ideal domain? Aniket.
Every ideal is a principal ideal.
Yeah, correct. Every ideal is a principal ideal, then it is a principal ideal domain or not? Is the statement you said is correct or not? Last time I give you a counter example, like this is the what part? If every ideal of R is a principal, then R is a PID. I gave you a counter example for this, right? In last time, the first question of this practice assignment, I gave you a counter example for this option. Do you remember this? Okay, try to remember and tell me. Muthukumar, is your definition correct or not?
Every ideal is generated by single element. That is what we call principal ideal domain.
Okay, is it principal ideal domain? So is okay. So if this is a principal ideal domain, is Z mod 4 is a principal ideal domain? Every ideal is a principal ideal here. You can prove.
Then it is a principal ideal domain.
Where it is domain, is this a domain? Why you are saying it is a domain? 2.2 is 0, right?
You
But
mean, first of all, that must be an integral domain?
Yeah, that's the thing you should remember always. It should be integral domain, then it should be every ideal should principal ideal. Otherwise, if every ideal is a principal ideal, then it is only a principal ideal ring, not a principal ideal domain. It should be domain also, right? So try to remember the definition correctly. Okay, the first option is this one. I is an ideal of R, then the question ring R mod I is a PID. So is this true or not? Tell me. Someone can reply. If I is an ideal of R, then the quotient ring R mod I is PID or not? If yes, then give me a proof. If not, then give me a counter example. Sarang, do you have any idea how we will proceed?
Thinking about one counter example, Z mod X with the ideal generated by 2.
ZX mod ideal generated by 2. Okay. So what? Okay, ZX mod 2 ideal generated by 2 is Z mod 2X precisely. You can prove this one is isomorphism. So Z mod 2X is a PID, right? Z mod 2 is a field, so Z mod 2X is a PID. So this is not a counter example.
Okay.
Yeah. So try to think something else if you are thinking about some counter example. Why 2? Think about some other ideal, right? 2 is a prime ideal. It have a nice properties. Think something else. But you are going in a right direction. Muthu Kumar, do you have any idea? Nagmani? If you don't want to unmute yourself, then why it is an interaction session? So if you don't want to interact, why it is a doubt session? You are not even asking a single doubt in any session. I'm just trying to give you some flavor of exercises, and even then you are not interacting. So it's not a good thing, right? You are not learning anything from here. You should interact with me. Then only I can understand what you are understanding and what you are not understanding. So it's not good. So, but you are thinking in a right direction. Like take R is equals to ZX, but you take I ideal 2Z. Take something else. Take something else. Then can you say something?
If you take simply Z and then you take 4Z, the ideal generated by 4, then you will have counter example because Z is a PID.
Right. Correct. So if I is an ideal of R, then the quotient ring R mod I is a PID, he is saying. But you gave me a counter example, and this is correct. This is correct. This is a false statement. So counter example is this one. Like he gave. Take ring is equals to ring of integers and I is equals to 4Z. Then this is a PID we proved in last lecture. This is a PID and I is equals to 4Z. I is equals to 4. The ideal is 4Z. Then R mod I is Z mod 4Z, which is isomorphic to Z4, which is by definition Z4 maybe. Yeah. So, but this ring is a not an integral domain. Integral domain implied not PID. So this is a false statement, right? Okay. So okay. Let's second part. If I is an ideal of R, then the quotient ring R mod I is a PID if and only if I is a prime ID. So if I is an ideal of R, then the quotient ring R mod I is also PID if and only if I is a prime ID. Tell me, is this true or not? Is this true or not? If true, give me a proof. If not, then give me a counter example. Uday Shankar, is this true or not?
I think it is true.
This is the proof, sir. Z7, certain groups, Z7 is a prime number.
Yeah.
Yeah, Z7 is a prime ideal also.
What you are saying, can you please say again? I didn't get you. I guess you are saying something wrong. That's why I am asking you. You can say again. Uday Shankar. There is something in chat box. If I is a prime, then R mod I is an integral domain, but not sure of PID nature. Okay. So that is the obvious one. Like if I is a prime, then R mod I is an integral domain. But you have to use that R is a principal ideal domain, right? This statement is true in general for any ring that R mod I is an integral domain if I is a prime. But here R is a specific ring, is a principal ideal domain. So how you can use that property? Try to think in that direction. So Muthukumar, you are saying something, right?
I think the result is true.
So how we will prove? If I is an ideal of R, then the quotient ring R mod I is PID. Suppose forward implication you are proving, then R mod I is PID. So how you will claim I is a prime ideal? That is obvious one, right? If R mod I is PID, that means it is integral domain. That means I is a prime ideal, right? This implication is obvious. Suppose the converse one, like I is a prime ideal and R is a principal ideal domain. Then R mod I is a principal ideal domain. You have to prove. How you will prove? Suppose J is any ideal which contains I. That means like J is any ideal in R mod I. So you just want to lift off this in R and then want to use the principal ideal domain property of R. Means you want to show this is a principal ideal ring R mod I because it is domain by definition since I is a prime ideal. So R mod I is a integral domain. So you just want to show it is a principal ideal. So now I gave you enough idea. Someone can say something now, right? Now you have idea that this statement is a true statement, but how to proceed? Someone should say me. Then I am happy.
Do we use correspondence theorem here?
Yeah, exactly. We have to use correspondence theorem. Okay, so how you will use?
You stated that J is an ideal that contains I in R.
Suppose let's take J is an ideal in R mod I. Then how you will proceed?
Then we have to find an ideal in R
Okay.
that contains I. The correspondence theorem will give us that.
Exactly. The correspondence theorem says that there exists, if J is an ideal in R mod I, then there exists an ideal J prime in R such that phi J prime means R to R mod I, there is a canonical ring homomorphism. Then phi of J prime is J. So you are just taking that ideal J prime, which is contraction of J. So that J prime is a principal ideal in R. So that principal generator image in R mod I generates J. So this is your argument. So did you get this or not?
Yeah.
Muthukumar, you get it or not?
Yes, it is okay.
Okay. So I should write it or it is fine? Okay. Let me write. Suppose forward implication first. Given that R mod I is PID. This implies R mod I is integral domain. This implies I is prime ideal. So we are done. Now for converse implication. Okay. Now for converse implication. Converse implication. Suppose, not suppose, given it is given. Given R is PID, I is prime ideal, Then to show R mod I is PID, how we will show? Okay, let J be an ideal in R mod I. This implies by correspondence theorem there exists an ideal J prime in R such that phi mapping R to R mod I, phi of this ideal J is equals to J prime is equals to J. Then since R is PID, this implies J prime is generated by some x belongs to R. This implies J is generated by phi x belongs to R mod I. So this implies R mod I is principal ideal ring but since I is prime, this implies R mod I is PID. So we are done. This is fine, right? Any doubt? You can say yes or no. Okay. The third part. Any ascending chain of ideals in R stabilizes. R ideals in R stabilizes. So tell me, do you understand the meaning of stabilizes? Chain of ideal stabilizes means that there is a, suppose this is the ascending chain. I1 contained in I2 contained in I3, so on, so on, so on. This terminate at some stage means like In equals to In plus 1 equals to In plus 2, so on, so on. Yeah. So tell me, is this true or not? Given that R is a PID.
Any PID is Noetherian.
Any PID is Noetherian. Okay. So how you will
Yeah.
argue for that?
So
Tell me.
every ideal in PID is generated by single element that is finitely generated.
So it's PID, right? So Noetherian, for Noetherian, there is a if and only if condition. A ring is Noetherian if and only if every ideal is finitely generated. So in particular in PID case, every ideal is principally generated by a singleton element. So it is finitely generated. That's why this chain should terminate. So any ascending chain of ideals in R stabilizes. So that's why it is true stable. Correct. So this one is true. What is justification? What is justification is R PID imply every ideal generated by single element implies every ideal finitely generated implies Noetherian, which says ACC. That's why. This is the argument. So now last part. Any descending chain of ideas in R stabilizes. Is this true or not?
No,
Why?
you can take in Z, you can take ideal generated by 2, 4, 8, and so on, all the powers of 2.
Okay. All the powers of 2. Okay. Then it will give you an infinite descending chain. Okay. How you will claim it is not stabilizers? How you claim it is infinite?
If it has to stabilize at one point, we will have in is equal to in plus 1.
Right. So what?
But we can say that at that stage 2 power n is not contained in 2 power n plus 1 ideal.
Right. Correct. Yeah. That's why the argument proceeds. Okay. So this is false. What is justification? Justification is that take in equals to 2 to the power nz. So 2z contain in sorry. Yeah, it is correct. Right? 2z contains 2 square z. This is strict containment, not equality. Strict containment 2 cube z. Yeah. So, containment is strict since 2 to the power n does not belongs to 2 to the power n plus 1 z. So that's why. Now next question. So this one is done. All the parts are done. Now the practice assignment 6. So this one is saying determine true or false. Second question. Determine or false. If R is UFD, and S is a subring of R. What is a UFD? Someone can say definition of UFD. Tell me what is a UFD? Is this true or false? We have to determine. Do you know definition of UFD or not? Tell me yes or no. Muthu Kumar, do you know definition of UFD?
UFD, first of all, is an integral domain.
Okay. Then what? Nipun, do you know definition of UFD?
Unit factorization should exist for all the elements in the integral domain.
Okay. So what is the factorization?
we can rewrite the element as a product of irreducible elements in the ring.
Okay, nice.
Meaning it is like a finite product.
Yeah, correct. It should be finite, right? Then it is a factorization domain. An integral domain in which factorization exists, that is a factorization domain. Now that factorization should unique in some sense, right? So means if there are two factorization, then terms should be associated to each other, right? So that is the definition. Let me write. If okay, there is someone who write definition. No, Nipon. So okay, let me write a definition for UFD. Okay, what is UFD? UFD. So first of all, you need to understand what is a factorization domain. Factorization domain. So what is a factorization domain, right? So what is a factorization domain? Okay, let me write definition. Let R be an integral domain. Then R is said to be factorization domain if R every element A belongs to R can be written as a finite product of irreducibles and a unit. Okay, so tell me, so before giving a factorization okay, let me give an example of a factorization domain and example of a domain which is not a factorization domain. So someone can tell now. First give me an example of a factorization domain. That is easy, right? Example Z in ring of integer. Every integer you can write as a product of prime powers, right? Agreed or not? This is basic fact. At least this you should know. Otherwise, what I can say? Muthukumar, do you know?
Z is UFD.
Yeah. So how you will say it, it is UFD, but how you will say every element can be written as a product of irreducibles, because every element can be every integer can be written as a product of prime powers, right?
Yes.
Yeah. So that's why.
Uniquely expressed as product of primes.
Yeah. So tell me now, what about a example of a factorization domain? Example of a factorization, sorry, example of a domain which is not a factorization domain. Tell me. I guess this is done in your class. He gave you a nice example.
ZX is not
ZX.
is UFD.
Yeah, it is UFD, right? If Z is a UFD, then ZX obviously is UFD. This is just a corollary of Gauss-Lamp. If R is a UFD, then RX is a UFD in Z. So give an example. Are you doing your classes? Because this was done in your class. I just see your notes.
You're asking for a counterexample to UFD or a factorization?
Factorization domain.
This one is Z of root 2, fourth root of 2, eighth root of 2, and so on.
Okay, you are saying fourth root of 2, eighth root of 2. So give me an example. Which so what is the element which you are saying not a factorizable element, which cannot be written as a finite product of irreducibles?
The element 2, you can write that as root 2 into root 2, but each root 2 you can write as fourth root of 2 into fourth
Yeah,
root of
that
2
is the
and so on.
correct idea. What about 2? Why you can take this thing as a 3? Then you can take like square root 3, fourth root 3. Then you can continue in similar manner, right?
Yeah.
Same for 3 also.
Z of root of minus 5.
Z of
Root minus 5.
okay. So claim that this is not a factorization domain. How you will claim? Give me an element which does not have factorization.
2 into 3 equal to 6
Okay, 2 dot 3 equals to 6.
equal to 1 plus root of minus 5 into 1 minus root of minus 5.
Okay. So what?
1 minus.
Okay, sorry, yeah. So yeah, it is minus. So what? So what? Tell me.
Because 6 is
It is a
expressed.
6 as a factorization, right? I don't
Six.
I don't care about uniqueness. I just saying definition of factorization. This have factorization. This doesn't matter for me now that the factorization is unique or not. But this have a factorization. The only thing matter is the factorization. This have a factorization. Like it can be written as a finite product of irreducible. So how you are saying it is not a factorization domain? This one is not correct. So otherwise, give me an example. If you are saying this is not a factorization domain, then give me an example. Otherwise, prove it. This is easy example. You can prove that every element has a factorization. Yeah, this one is similar, man. This one you can write infinite product. And this is 8th power product and so on. So this is the example of a factorization domain, which is sorry, example of a not factorization integral domain, which is not a factorization domain. So now
Fourth root of 2 4 times.
Yeah, this one should be yeah, it should be 4 times. Fourth root of 2, fourth root of 2. Then now yeah, similar way. Continue. Similar way. So yeah. Now what is a unique factorization domain? Now the Muthukumar's example will come. But first tell me definition of a unique factorization domain. First of a unique factorization domain. A factorization domain is unique factorization domain if the factorization is unique. So what is the meaning of unique? Can someone say what is the meaning of unique? Suppose A belongs to R and A have two factorization. A equals to P1, P2, Pn. This is the product of irreducible and is equals to Q1, Q2, Qm. So what this means is that M should be equals to N and Pi. What is Pi? What is the relation between Pi and Qi? Okay, tell me.
Pi and Qi will have to be associates.
What is the meaning of associate?
Their Pi has to be equal to some Qj into U because again order may not be same. Meaning
Pi should divide Qi and Qi should divide Pi, right?
Yes.
That is the meaning of associate. Yeah, there should exist some units such that Pi equals to Qi dot. You are Pi should be associate to Qj for some j. Yeah. So okay, now Muthukumar's example come. Give me an example of a unique factorization. Example of a factorization domain which is not a unique factorization domain. That is the example which Muthukumar gave. Like the factorization is not unique. You can see that 2 and 3 both are irreducible and 1 plus root 5 and 1 minus root minus 5 both are irreducible. But the factorization is not unique and they are also not associated. So that is the example. So now come to our questions. So this is just a definition which I need to introduce for this question. So if R is UFD and S is a subring of R, then S is a UFD. Now Nipun will tell me that is this correct or not. Where is Nipun? Yeah, he's here. So Nipun, you tell me, you asked me definition, I gave you definition. Now you tell me, is this statement correct or not?
One question regarding S. Can I ask?
Okay, what is the question?
In the beginning of the course, it was mentioned that all rings that would be considered in the course will be commutative rings with unity.
Exactly. All rings are commutative ring with unity.
So 2Z will not be a ring, right?
Right, it will not be a ring.
Okay. Because if you consider like that, then Z and 2Z will be like a example, because if I take 4 in 2Z, I can factorize it into 2 and 2 and minus 2
Why
and minus.
2Z is also UFD? Why 2Z is not UFD? Tell me.
Meaning we have 2 and 2, minus 2 and minus 2.
But they are associated, right? 2 and minus 2 are associated, right?
But not in 2Z, right? Because my
Oh
1
yeah,
and minus
there
1
are
are
not
there.
units, right? Oh yeah, you are correct, but that example not work here. Yeah, right. So think about something else, because the definition given to you is that subring should contain unity also. Nipun, you want to say something? Okay, so if you don't have any idea, let me say. Okay, so if R is a UFD and S is a subring of R, then S is a UFD. Someone already give me an example, right? If you does not. Okay, Nipun, you are not audible, so leave it. The statement is correct. Okay, you are asking to me or saying that it is correct. Okay, let me say the statement is not correct. If R is UFD and S is a subring of R, then S is a UFD. Someone gave me also a counter example, but that is not according to your course notation, because in your course the instructor assumed that the subring should contain unity. Like you define ring as a commutative ring with unity, right? The definition of a ring. So S should contain unity also, but you gave me a good example, right? In ring of integer, if you does not include in definition unity, then 2Z is a subring of Z, but which is not a UFD. So right. So but you have to think something else. You know Z root 5. Okay, example. You know Z root sorry minus 5 is not UFD. This one you know. So now include it in some field. ये किसी न किसी it will sit inside some field, right? You can sit this inside q root minus 5, and you know this is a number field, means it is a field. This is a field. Now this is a field. This means this is a principal ideal domain, even Euclidean domain, everything nice. PID, ED. So that means it is a UFD. So you give, and this Z root minus 5 is a subring of this q root minus 5. So it is a subring, but not UFD, right? And the ring is UFD. The candidate of R is this one. Candidate of S is this one. So do you agree with me or not? Do you have any doubt?
Even if you take C also for Z of root minus.
Yeah, that will also work, right? Root minus 5. Yeah, that will also work. So I hope this is fine. So now next one. Now the second question says, if R is a UFD, choose all correct statements. UFD, choose all the correct statements. The first one is any irreducible element of R is prime. Tell me, is this true or not? Muthukumar, is this true or not?
I think it is true.
Okay. So what is the idea? This is a standard statement. I guess it should be done in your class. A factorization domain is UFD if and only if every irreducible element is a prime. True. Okay, someone is saying true, correct. So let me write a statement here and I will black box this statement. Its proof is slightly tricky. I will not do this one. Okay. But this was done in your class. I see your notes, so that's why I am not doing. So let me black box here. Let R be a factorization domain then R is UFD if and only if every irreducible element in is prime. But in last interaction session, we see that every prime element in an integral domain is always irreducible. So now over UFD, every irreducible element is prime. In last class and in last interaction session, we proved that in over PID, every irreducible element is prime. But now this statement is saying over UFD, every irreducible element is prime. So by this statement, by this fact, theorem, you can say this is a fact. This is the true one. Any irreducible element of R is prime. Since it is UFD. Yeah. So the second one, if I is an ideal of R, then the quotient ring R mod I is also UFD. I is an ideal of R, then the quotient ring, then the quotient ring R mod I is also UFD. Right. So tell me, is this true or not? Some ideas, approaches.
I mean, I is an ideal of R, so elements in I are also it can be uniquely factorized with
Yeah.
respect to R.
Yeah.
We have to form somehow we have to write the like all the irreducibles of all the elements in I, something like that.
Okay, you are claiming the statement is true, right?
Yeah.
Yeah. So okay. So what is the idea? Suppose you take any element X in R mod I. You are saying its factorization is unique here.
Yeah.
So how you will argue?
The image of any element under the canonical homomorphism R to R mod I. If we consider that, then any of the irreducible elements that occur in any element in I have to go to 0 in R mod I, somehow like that.
Okay, tell me again, what is your argument? Suppose you take element X bar in R mod I. How you will claiming its factorization is unique?
So it will have a pre-image in Rx.
It will have a pre-image in right? It will have it. This is a surjection. Okay, so it will have
Yeah.
a pre-image.
Yeah, X is in R and R is a UFD. So so X will have an unique factorization in R.
Yeah.
When we take the image to R mod I to X bar,
Mhm.
if we look at all the elements in I,
But the pre-image is unique or not? Like why it should be unique? Suppose you take element of some element of I, then x plus I can be written as x plus a plus I. Then x plus a have different image in R instead of x. It can have different. So why how you will guarantee uniqueness of the such kind of factorization?
okay,
Even if it will introduce some factorization, how you can guarantee that this will be unique, right?
so
And
there is some ideal in a UFD such that the uniqueness is lost.
yeah, it should, right?
Okay.
Like Z is UFD, right?
Yeah, Z is a UFD, then any ideal will be PZ. No, NZ.
Yeah, yeah.
PZ will be the prime
But
ideal.
Z mod and Z need not be UFD, even it need not be integral domain, right?
Oh, yeah. Okay.
So why it should be UFD? Did you get your point? Where you are wrong?
Yes.
Yeah.
So I is an ideal, you need more structure for that.
Okay. So let's see. The next statement will say something more. So this is false. So what is the example? Example: R is equals to Z, I equals to NZ, and not prime. This implies Z mod NZ is not UFD, right? Not even integral domain. So now, as you are saying, do we need some more structure on I? So what about if I is a prime ID? So next question, I guess, should come in this direction, right? So if I is a prime ideal of R, then the question like R mod I is here. I is a prime ideal of R, then R mod I is UFD. Okay, tell me, is this true or not? Even this is not true, means, right? Like last time I gave you some example where it is not integral domain, but now it will be integral domain, but uniqueness will fail somewhere. Like I say you in your mind, the uniqueness are getting failed somewhere. So now tell me, what should be counter example for this? Or if you are claiming a proof, then claim your proof. What is your proof? Okay, sir, I have not covered this week's lecture, so may I leave? I am not getting these right now. Okay, yeah, you can see recorded session, no problem.
We cannot use Z as a counter example here because
Yeah, we cannot use, because if you take some prime ideal, then Z mod PZ is a field, so it will be UFD. So you cannot use Z. Think something else. If Z is a UFD, then ZX is also UFD. I guess you know this statement, right?
yes.
Yeah. So ZX is UFD. Okay, so you can think about some prime. Okay, so think about this connection. ZX here you have Z root minus 5. You have to find some ideal I such that ZX mod I is isomorphic to this ring, ZX mod I. So tell me, what should be that ideal? I gave you enough, right? I should be prime ideal.
Then we need one. I has to be. It will be generated by x squared plus 5.
Yeah, that is correct,
Okay.
right? But how you will claim this is a prime ideal?
X squared plus, if it is not a prime ideal, then for any
Ideal
we have to look
generated
in
by
Z of X, right? Z of X, basically, if X squared plus 5 is prime in Z of X.
x square plus 5, you can prove this is irreducible, right?
Yeah, so as a result, yeah, irreducible is prime. So
Yeah, irreducible is a prime, so it will generate a prime ideal, right?
yes.
Yeah. So how you will prove x square plus 5 is irreducible? Now here you have to prove. Claim x square plus 5 is irreducible in Zx. How you will prove? Do you know Eisenstein criteria?
So we have to use Eisenstein's criterion for P equals 5 here.
Yeah,
So
Eisenstein criteria. So choose P equals to 5. So what?
so we have to look at the coefficients of X squared plus 5.
Yeah.
We,
So
we
P.
can treat.
So what is a naught? A naught is 5, right?
Yeah.
A1 is 0 and A2 is 1 and others up to A2 is needed, right? So P should not divide AN, right?
Yes. It will divide all the other coefficients.
Yeah, AN equals to 1 and P does not divide A. And P should divide A0 and A1, right? P
Yes.
divides A0 because A0 is 5 and P divides A1 because A1 equals to 0, right?
Yes.
And P square should not divide
A0.
Yeah. P square is equals to 25 does not divide A0, which is 5, right? So that means this says that x square plus 5 is irreducible in Qx.
Okay.
So how you will guarantee this is irreducible in Zx?
If it were irreducible in Z of X, then I get one non-trivial breakup into two irreducible elements in Q of X, which is a contradiction to what we got from Eisenstein's criterion.
Yeah, correct. Okay, what you are
No,
saying?
if it is irreducible over Z and if it is primitive, then
Yeah,
it is
what you are
irreducible.
saying, what he is saying also correct, right? Well, you are using some statement like if it is a primitive polynomial, then you can say if it is irreducible in Qx, then it is irreducible in Zx. You are saying this one, right, Muthukumar? Muthukumar, you are saying this statement?
Yes, if it is irreducible over Zx.
Yeah, let me write your statement. Muthukumar is saying,
Irreducible in Zx, and if it is primitive,
yeah,
then it
Muthukumar,
is irreducible over Qx.
yeah, Muthukumar is saying something. Fx belongs to Qx is irreducible over Zx if and only Fx is primitive. Fx belongs to Zx. Sorry, what I am writing. Zx is irreducible over if, okay, what I am writing. If Fx belongs to Zx is irreducible over Qx, then Fx is irreducible over Zx if and only if Fx is primitive. Okay, so do you know definition of primitive? Muthukumar?
Primitive, the highest, the n greater than 0 and an greater than 0, and the greatest common divisor of all the coefficients must be 1.
Yeah, correct. So if Fx is equals to your polynomial, say this one, a0 plus a1x plus a2x square plus so on an x to the power n, then it is primitive if n greater than 0, an greater than 0, and GCD of a0 so on an should be 1. So right, so in this polynomial x square plus 5, n is greater than 0 because it is 2-degree polynomial. An is equals to 1, a2 equals to 1, so which is greater than 0, and GCD of 1, 0, 5. What is this?
Is 1.
1, right? So this is a primitive polynomial. So this is a primitive polynomial. So for x square plus 5, this implies x square plus 5 is irreducible over zx. Okay, nice. We prove that this is irreducible over zx. So over UFD, irreducible imply prime, and this is a generated prime ideal generated by prime ideal. So this is a prime ideal. So now you are claiming that this ring is a canonically isomorphic to this ring. Both rings are same, even I say. So how to say this? Can someone see something or say something about this? Muthukumar, do you want to comment something? Or Nagmani or someone, anyone can comment that, right? Sarang.
You can try the evaluation homomorphism and prove that it is an isomorphism.
No, not necessarily. Let me write explicitly. Zx, what is this? Zx contains the polynomial fx is equals to a0 plus a1x plus so on an x to the power n. N belongs to natural number union 0. An belongs to z, right? Agreed or not?
Yeah, but I was actually saying evaluation homomorphism from Zx mod x squared plus 5.
What will be the evaluation homomorphism? Okay, everything you are evaluating at root minus 5.
Huh?
Everything you are evaluating at root minus 5. What is your homomorphism?
Yeah, so it will go to root of minus 5, correct?
Yeah. So that is correct also. In that way, you can also say isomorphism. But I want to see you by show you by structure. So zx mod x square plus 5. What is this? So what is this ring? Fx belongs to zx such that x square plus 5 you are treating as 0. That means
Oh yeah, correct. All the elements which you want to show that
Yeah.
are 0 are.
Yeah, so it should be same as x is equals to plus minus root 5, right? Either I take plus root 5 or minus root 5, it doesn't matter, because I can, if I choose plus root 5, I can choose a1 equals to minus a1 choice for that, right? All polynomial come there, right?
Okay.
Yeah, so it is enough to me choose plus root 5, because if I will choose x to be plus root 5, then I can obviously include x to be minus root 5 there, because choosing a1 equals to minus 1, right? Yeah, so all polynomials, how they will look like? A0 plus a1 root 5 plus a2 root 5 square, but that is 5, plus a3 root 5 cube, that is 5 root 5, and so on, plus so on, but at finite terms. But what is this where a0 and a1 belongs to z? Okay, I'm writing some non-intuitive way. a1 not comma a1 belongs to z comma a2, so on, all belongs to z. So what is this? Now you can merge these all terms, right? A2 5 is in integer, because A2 in integer and 5 is in integer, and A0 is in integer. Similarly, you can merge this all integer terms and you can write this as A0, right? Write this as a B0, like B0.
X is equal to plus or minus root of minus 5 or root 5?
Plus root, okay, sorry. Root minus 5 plus minus 5. Yeah, here you should write minus. This is plus, this is minus. Yeah, this way. Yeah, so this one should be like b0 plus, merge all these root minus 5 terms. This is b1 root minus 5, where b0 comma P1 belongs to Z. And this is same as Z root minus. This is by definition even. Z root minus 5 you define in this way, right? What happened? Agreed or not? Sarang,
Yes.
you
Yes.
agreed
Yes.
or not?
Yes. Yes.
And what Sarang is saying is also correct. Sarang. Whatever. You are saying that define a evaluation map from here to here. X square plus 5 to Z root minus 5. Defined by phi of fx is equals to e naught plus a1
Ideal generated by x squared plus 5.
root minus 5 plus a2 root minus 5 square plus so on so on so on an root minus 5n, where fx is equals to a naught plus a1x plus so on so on so on so on an x to the power n. So check this. This is a ring homomorphism. This is obvious check. Sorry, ring isomorphism. Check. This is ring isomorphism, right? So nice. We get this one. What we have to say? We have to give an example of a prime ideal such that R is a okay. R mod I is a not UFD, but R is a UFD, right? So we take ZX, which is a UFD, and ideal x square plus 5 generated by x square plus 5, which is a prime ideal, but R mod I Z root minus 5, we know this is not UFD. So this one is a false statement. Sarang, now you agree with this or not?
No.
Okay, what is your doubt?
Oh, no, no. You were saying about the statement.
Yeah, I'm saying like initially you are saying this should be true. Okay, so you agree now or not?
I agree that it is not a UFD.
Okay, so did you get this proof?
Yes, it is clear.
Okay, nice. Okay, so next part. Okay, the fourth part here is any ascending chain of principal ideals in R stabilizes. Any ascending chain of principal ideas Okay, tell me, is this true or not? Any ascending chain of principal ideas in UFD stabilizes. Someone want to say something? Comment something? How we will proceed? Nagmani, how we will proceed? Okay, no one want to say something? Let me write. Any ascending chain of principal ideas in R stabilizes. So this is a true statement. Not even for it just a factorization domain needed, not even UFD. So how you will claim this? Principal ideas in R stabilizers. Suppose I1 is generated by A1, this is A2, so on, I3 is A3, so on, so on, so on. So now see, A1 belongs to ideal generated by A1, and this is contained in ideal generated by A2. So that means A1 belongs to ideal generated by A2. This means there exists B belongs to R such that A2 equals to, sorry, A1 belongs to A2. So A1 is equals to BA2. Now A2 belongs to A3, right? This one contained in here is I3. So this one is contained in A3. So that means A3 is equals to, I should index this one, right? B1 belongs to B1. Now there should exist some B2 such that this implies similarly there exists B2 belongs to R such that A2 is equals to BA3.
B2A3.
Yeah, B2A3. Similarly, there exists B3 belongs to R such that A3 is equals to B3 A4. Continuing similar fashion, we get similar fashion. So what is A1 equals to BA2, right? And now put the value of A2. This is B2 A3, B3 A4. So you get B1, B2, B3 infinite expression, and B1, B2, B3, so on, so on, so on. And this one, uh, at the end, you will get like this one is an infinite expression, B1, B2, B3. Then you are factorizing every term. So this is an infinite expression, and some, like you can say some, yeah, this is an infinite expression, infinite product. Contradiction to the fact that R is UFD. This is happening to them. Okay, so this contradiction to fact that R is UFD, this implies the chain of ideals stabilizes at finite state. Okay, so what we prove? Where is that? Yeah, this one. So this containment, if this containment is strict, we prove that we will get an infinite factorization, right? So so this chain should stabilizes at finite state, right? So we are done. So this one is a true statement. True. Okay. Now next one. Choose all correct statements. Fourth question.
Excuse me, you are getting A1 equal to B1, B2, B3, etc.
Yeah.
From that, how you say that the chain stabilizes at a finite stage?
I get a contradiction, right? I assume the chain is infinite ascending chain, which is a strict inclusion, right? I1 is strictly contained in I2 is strictly contained in I3. So I will get this infinite product, right? A as an infinite product, like A1 equals to B1 A2, then A2 equals to B2 A3. Then put the value of A2 there, then put the value of A3 there, so on, so on, so on. So you will get an infinite expression, but which is a contradiction to the factorization property of UFD, right?
You have constructed an element in the ring such that it is not uniquely factorizable from the
Not
chain.
even factorizable. No, I did not guarantee uniqueness. I am saying that it is not factorizable. I took the generator of the ideal I1 and I claim that it is not factorizable.
Okay.
Yeah. Agreed, Muthukumar? You
Okay,
agree or not? Yeah. So if R is a PID, then R is a UFD. First. Okay. Tell me, is this true or not?
So this is true.
How you will argue? Above, in first or second question, I stated some fact like if factorization domain is UFD, if and only if every irreducible element is prime. And in last lecture, I proved that over PID, every irreducible element is prime. So R is UFD, right? What is justification? So R is PID. This implies Noetherian. This implies ACC. So this implies factorization domain. Noetherian domain. Ascending chain condition satisfied. So this implies factorization domain. And what about other property? So using the fact if factorization domain R is UFD if and only if the irreducible element is prime. So only need to show so need to show every irreducible element in PID is prime. But I guess this I had done this proof in last time. Muthukumar, do you remember I did this proof last time? No. Okay, let's do this proof. He is not saying anything. So claim this is. So how we will prove? Suppose A is an irreducible element in R, right? Want to show A is prime. So prime means A divides BC, then A divides B or A divides C, right? We want to show this. Okay. How we will prove this? Okay. Suppose A does not divide B. Now, since in last session we proved in PID GCD exists, right? So how we can use this? Let's choose the GCD of D equals to GCD of A comma B. Then how you can argue? Then D is equals to GCD of A comma B. So D divides A and D divides B. Okay. So what? How we will argue? So A divides BCD. Okay. A equals to BC. A is an irreducible element. So right. A is an irreducible element. Okay. How we will use that one? Right? Let me think. Wait a second. Any idea how we'll proceed? Muthukumar, do you have any idea?
We want to prove A divides C.
Yeah, I want to prove. Like A divides A does not divide B. I assume I have to prove that A divides C. Okay, this one is easy, right? So D GCD of A divides BC. Okay, so A is an irreducible element. What is irreducible mean? A equals to BC. Then either B unit or C unit. B unit or C unit. So we have to prove A, want to show A is prime. So yeah. So A divides BC, then yeah, A divides BC, and A divides B or A divides C, right? So how we will proceed? D divides GCD of A comma B. So D divides A, D divides A, right? So either B unit or C unit. It does not divide. Yeah, it remains some subcases to prove. Okay, let's black box this statement. Maybe I can do this one is next time. Show that, yeah, it is easy statement, but I don't know why it's taking me some time. I guess this will be done in your class. I guess this should be done. This is a basic statement. Yeah. So let's black box this one. Do next time. So assume this one, every irreducible element in PID is prime. I means this is series statement. So yeah, I guess I proved in last session also, but at this time I'm studying in this one. So maybe we can see next time. So every irreducible element is prime. So what we want to conclude from there? Yeah. So we proved that every irreducible element is prime. So this implies since every irreducible element element is prime, this implies, and R is factorization domain, this implies R is UFD. So we are done. So what we have to prove? If R is a PID, then R is a UFD. We proved this one. Right. So now next one. If R is a UFD, then R is a PID. Tell me, is this true or not? Someone can unmute yourself and can say something, right? Debasis, you want to comment something? This is UFD. If R is UFD, will this be PID or not?
ZX is
If
UFD,
not-
but ZX is not PED.
Okay. So what is the ideal which is not principal ideal?
Call from 09566 18613.
Okay. Muthukumar gave me example. So take R is equals to ZX and R is equals to ZX, then R is UFD but not PID. Take I is equals to ideal generated by 2 comma x, right? So this one. Yeah. Now the last one. Okay, this is the third one after this one also. So the statement is false, right? After this, the third one. Every non-zero prime ideal in UFD is maximal ideal. Maximal ideal. Is this true or not? This is not true. So take the ideal I is equals to ideal generated by 2 in ZX is prime since ZX mod ideal generated by 2 is isomorphic to Z mod 2x, which is integral domain. That implies ideal generated by 2 is prime. So this is prime ideal but not maximal. Not maximal since ideal generated by 2 is contained in but not equal to ideal generated by 2 comma x. So yeah. Now the last one, every non-zero prime ideal in a PID is maximal ideal.
that ZX in C, ZX is not UFD. The statement is every prime ideal in UFD is maximum.
Yeah. Yeah.
What ring you have taken and what ideal?
Ring is ZX and ideal is ideal generated by 2, which is prime ideal I claim, and I prove this is prime. Then I claim that this is not maximum.
No, because prime ideal in UFD, but ZX is not UFD.
ZX is why it is not UFD. It is not PID, but it is UFD. If R is the UFD, then RX is UFD.
Oh, sorry, ZX is UFD but not PID. Okay. Okay.
Yeah. So now the next statement: every non-zero prime ideal in PID is maximal ideal. So is this true or not? Tell me.
This is true.
Okay, Muthukumar is saying this is true. So argue how is this true? Suppose P is a prime ideal. Prime ideal. Then to show P is maximal, I will say this is maximal. Tell me. Now you are inside PID. Suppose this is not P contained in I. Suppose strictly contained in I. So I should be also principal, right? So I should be generated. This will be generated by some element B. This will be generated by some element, say A. Then what? Then what? That means A is equals to. That means B belongs to ideal generated by A. That means B is equals to AC for some C belongs to R. Right. So what you can say from here? Since you are inside PID, so this ideal generated by B is a prime ideal. So B should be prime element. So if B is a prime element, then B divides AC. B questions B equals to AC. This implies B either divides A or B either divides C, right? Then what? If B divides A, that means A is equals to BD. That means B is equals to BDC. That means B dot 1 minus CD equals to 0. But since we are inside the integral domain and B is non-zero, that means CD equals to 1. That means C is unit. So if C is unit, so that means B and C, A and B are associated. This implies ideal generated by A is equals to ideal generated by B. Sorry, ideal generated by A equals to ideal. That means E is maximal. We are done, right? So every non-zero prime ideal, every non-zero prime ideal P is maximal. So this one is a true statement. We prove. So with this, this assignment is also complete. This 6th one. So now we have some time remaining, half an hour. So let's see some other thing. Okay, do something like you have to see the ascending chain condition for Noetherian ring. Let's introduce some ring which have some descending chain condition, and that will be some there will be some property. Okay, so analogous, sorry, ring which seems similar, opposite signs, to Noetherian rings. With this we are done here. To Noetherian rings, but have more nice properties than Noetherian rings. These are namely Artinian rings. These are the closed enough to fill. Closed enough to fill. Okay. So, okay. So what is the Artin ring? We have to write first definition, right? So what is the Artin definition? So what is an Artin ring? So in Noetherian ring, we see the the ascending chain of ideals should terminate. So here, a descending chain of ideals should terminate. The ring R is said to be Artin ring, Artinian ring, if it satisfies descending chain condition. What is the meaning of this? So if I1 contained in I2 contained in so on, this one is descending chain, then this should stabilize at some finite stage. Okay, so this is the definition which I just want to introduce. So see some nice property of this ring, right? So let's introduce some statement, proposition you can say, and then you will get the flavor of this and how nice this is. In Artin ring, every prime ideal is a maximum. In an Artin ring, every prime ideal is maximum. So, do you know Noetherian ring, right? So in Noetherian ring, is every prime ideal maximum? Someone can unmute yourself and say something. If yes, give me a proof. If not, give me a counter example. Nagmani, in Noetherian ring, every prime ideal is maximal or not? Devasis, you can unmute yourself. Muthukumar, is this correct or not? In Noetherian ring, every prime is maximal.
It's true.
This is true in Noetherian ring. Rx is a Noetherian. Okay, it is okay. So Rx is a Noetherian ring. So is every prime ideal maximal ideal? What about the zero ideal? Will this maximal? Okay. So you don't want to say something, so let me write.
Okay, maybe this is the main difference between Artinian and Noetherian.
Yeah, this will be also a different, but you can see other difference. Even you will see a more stronger statement that every Artinian ring is a Noetherian ring. We will prove. But every Noetherian need not be Artinian. So there should be some nice condition for the ring to be Artinian. So what is the here? In Noetherian ring, prime need not be maximal. Example, take R is equals to Rxy, then ideal generated by X is prime, but not maximum. This one. So now the proof of this statement. How will prove? So Muthukumar, do you have any idea how we will prove such kind of a statement? We have given a prime ideal and we have to prove it is maximal in an Artinian ring. So okay, let P be prime ideal of E of our ring R. P, what we write our ring? E or R? Artinian. Okay. Of R. Then what this says? P agar, if P is a prime ideal, then B equals A mod P is an integral domain. So this is an integral domain. So what we can say? We have to prove this is a field. Want to show B is field because P is maximal if and only B is field. So B is field. So what we will do? If we want to some ring to be filled, so if every non-zero element should be unit, right? So let's check. Let 0 does not is equals to X belongs to B, be some non-zero element. So what the descending chain condition? So by the descending chain conditions, at some point the descending chain should stabilize. This means that ideal generated by x to the power n should be x to the power n plus 1 and so on for some n, for some large n, because the chain should stabilize higher state. So what this is meaning? This means that x to the power n belongs to xn plus 1. That means x to the power n is equals to xn plus 1y, right? For some y in B. So what you can say from here? This implies x to the power n 1 minus xy is equals to 0. Now, since B is an integral domain, this implies and x non-zero, this implies x to the power n non-zero. So we have, so 1 minus xy should be 0. So this implies xy is 1 This implies X is unique. So I take any non-zero element in ring X and I prove that this is a unit. So this means B is equals to A mod P is filled. This implies P is maximal. Hence we prove that. Hence we prove every prime ideal P in an Artin ring is maximal ideal. So this is the interesting one. Okay. So now here is the some corollary for you. You will tell me how we will prove this. In an Artin ring, nil radical is equals to Jacobson radical. How we will prove this? Can someone say something?
Please explain Jacobson radical as well as nil radical.
Okay, you don't know this one? Okay. Nil radical, this Jacobson radical is intersection of maximal ideals of ring. And this one is intersection of all prime ideals. Prime ideals of ring. So this is the definition. Nil radical is intersection of all prime ideals of ring, and Jacobson radical is intersection of all maximal ideals of ring. So now you have to say that for Artin ring, nil radical and Jacobson radical are same. Can you
So
say?
in an Artinian ring, every prime ideal is maximal.
Yeah. So this one is a containment, right? So every prime is
therefore-
maximal. So this should, right?
Intersection of prime ideal is contained in every maximal ideal.
Yeah.
Sir, and the converse is also true, no? So both
Why?
will be equal.
Why? How you will say converse? Converse is always true, but you have to say me something, right? In a commutative ring with unity, converse is always true. Jacobson radical is always contained inside nil radical. Sorry, I am saying something wrong, I guess. Let me correct it. Let me correct it. Okay, let's write these things. Let's don't put containment directly, but let's type first and then put containment. What's happening? Oh, okay. Oh. Okay. Suppose P prime, this implies P maximal in Artin ring, since R Artin ring. So this implies any prime is a maximal, right? So intersections of primes is contains intersection of maximals. This one will be containment because every prime is maximal. So there can be some, this statement does not guarantee every maximal prime. So there can be some maximal ideal which shrinks down. So that will be not possible. But since in commutative ring with unity, every maximal ideal is prime, This implies intersection of maximal ideal is contained in intersection of prime ideal. Sorry, this one, yeah, contains intersection of prime ideals. This implies nil radical equals to Jacobson radical. Yeah. So for
Sir,
Artin ring,
Artin ring is always a commutative ring, no?
yeah, yeah. For
Yes.
this course, always commutative ring.
Okay.
Yeah. Okay. Now the next interesting statement is that claim proposition. An Artin ring has only finite number of maximal ideals. Is this true for Noetherian rings? Someone can say something. Is this statement true for Noetherian ring? Is Noetherian ring of every Noetherian ring have finitely many maximal ideals? Only finite number of maximal ideals. Is this true or not? Ravi Shankar, is this true or not?
Sir, for Noetherian ring,
Yeah, tell me. For Noetherian ring, is Noetherian ring have finitely many maximal ideals? Only finite number of maximal ideals. Muthu Kumar, is this true or not?
So you are asking whether this result, this is any Artinian ring has only finite number of maximal ideals.
Yeah, this is the result. This I will prove that any Artinian ring have only finite number of maximal ideals. I am asking to you that for Noetherian ring, is this true or not? Is Noetherian ring have only finite maximal ideal, finite number of maximal ideals? I am just comparing the result of Artinian ring with Noetherian ring. Whatever I am proving. Take the ring. Take the ring of integers. So how many maximal ideal you have there?
sir,
Infinite number of maximal ideals.
Yeah, that's what I want to hear from you. There are infinitely many number of maximal ideals because if maximal ideal correspond to prime numbers and there are infinitely many primes. I
Yes,
hope
sir.
you proved this in your high school. So there are infinitely many maximal ideals. So let's write here.
So, sir,
Comment.
for Noetherian ring, it will be infinite.
Yeah, Noetherian ring can have infinite number of maximal ideals.
Yes.
Noetherian ring can have infinite number of maximal ideals. What is example? Example is Z. So now prove this statement for Artin ring. How you will prove? We have to prove that there are only finite number of maximal ideals. So, okay. So definition, when you introduce this, there are all 2-3 equivalent conditions like ascending chain conditions for Noetherian, then it is equivalent to, it has some maximal element collection of ideas. These are all equivalent if statement. So similarly for Artin ring, there is an equivalent statement. There should some minimal element, right? Like in ACC, there should some maximal element. Here should some minimal element. So I will use that one here. Consider. Okay, let me write. You will get it. Consider the set of all finite intersections, all finite intersections M1 intersection M2 intersection Mn, where the Mi are maximal ideals. What happened?
Sir, screen blackout.
Yeah.
Okay, fine.
So where the Mi are maximal ideals. Yeah. So this set has a minimal element by this definition, since R is R-T ring. This implies this set has a minimal element, say M1 intersection M2 intersection Mn, suppose. So then what? Now you take any maximal ideal M. Now if you take any maximal ideal M, then what you can say about this M intersection M1 intersection M2 intersection Mn? Because this one is minimal, right? You choose this one is minimal, M1 intersection M2 intersection Mn. Collections in the set of all finite intersection, this is minimal element. So this one is also finite intersection, right? So since this one is minimal, see, this one is minimal, minimal among all finite intersection of mixed ideas, right? So this is minimal, but now this one will be always contained in this one, M1 intersection M2 intersection Mn. But since this one is minimal, so this should be equality, right? Since this one is minimal, so this will always consider this one, contained in this one. So this should be equality. So by prime avoidance lemma, okay. Now what? So what this says, if this happens, okay. So not now, but after this. So M should be contained in, okay. M should contain this one, right? M1 intersection M2 intersection Mn. So now since every maximal ideal is a prime ideal, so we can use prime avoidance lemma. So by prime avoidance lemma, M contains Mi for some I. But since Mi is maximal, this implies M equals to Mi. This implies there are only finitely many maximal ideals, namely M1, M2, so on, Mn. Only these are the maximal ideals. So we are done. So we proved that in an R10 ring, there are only finitely many maxima. Yeah. So this is the thing I want to say you.
Sir.
Yeah.
For the Arterian ring, their intersections should be minimal.
Yeah. There should some minimal element, like for Noetherian ring, do you know definition? There should be some equivalent definition. It satisfies that there is an ascending chain condition there should some maximal element. If you take any collection of ideals, that should have a maximal element, right?
Yes, sir.
Yeah. Similarly, here, if you take any collection, it should have some minimal element. So I am taking the intersection or finite intersection collection, finite intersection of maximal ideal collection. It should have some minimal element, right?
Okay, sir.
So by this condition, I am saying that this M1 intersection M2 intersection Mn is minimal element. So now this is minimal element.
So
if you,
it will be contained in that maximum ideal.
yeah. Now the thing is that M intersection M1 intersection M2 intersection Mn. Now we are intersecting with some other thing. So this is already small s. We are intersecting with some other thing which is still finite. This is still finite number of intersections. So this, since this M1 intersection M2 intersection Mn is smallest one, so this should be equality, right? Because one containment is obvious, because M intersection M1 intersection M2 intersection Mn is always contained in M1 intersection M2 intersection Mn. But since this M1 intersection M2 intersection Mn is small s, so this one is already contained in M intersection M1 intersection M2 intersection Mn. So both side containment we have. So this is equality. So now if this is equality, then M should contain or equal this one, M1 intersection M2 intersection Mn, right? So now since M is maximal for prime and Mi are all prime ideas because maximal ideas. So by prime avoidance lemma, what prime avoidance lemma says, if P contains intersection of prime ideals like P1 intersection P2 intersection Pn, then P should contain some of prime ideals, at least one of the prime ideals. So P contains some, M contains some Mi. So now, but since Mi is maximal ideal, it is maximal itself. So there cannot be any other ideal which contain it. It can be at most equals to this Mi. So M should be Mi. So now I take, since M is my arbitrary any maximal ideal, I prove that this should be sum of Mi, and Mi are only finitely many choices, 1 to n. So I prove that there are only finitely many choices for maximal ideal. So I prove that there are only finitely many maximal ideals, M1 intersection M2 intersection, M1 comma M2 comma Mn in an Artin ring. So this is interesting, right? So, okay.
Yes, sir. That prime avoidance lemma was an interesting one.
Yeah. This is in first chapter in Athiya McDonald. If you want to see, you can see its proof also. This is easy step. There are two versions of this. One is for union, one is for intersection. So you can see this one there. Maybe I can, yeah, but I don't have my Athiya, so I can. Okay, you can see this one there. Yeah. Wait a second. If I can open my Athiya. Okay. This should be somewhere here. Okay, this is the statement. Let me write for you this statement. Statement. Time avoidance. What is the statement? Let R be commutative ring with unity. Then first one, let P1, P2, Pn be prime ideals. Then what is the statement? If first one is same as this one which we use here, right? If if A and P contain, like, okay, let me write. So if A is any ideal contained in union of this Pi, then A contained in Pi. So if A containing union of I equals to 1 to n pi, then A contained in pi for some I. First one is this one, and second one is if P is any prime ideal such that P contains intersection of AI, where AI are ideals in R. This implies P contains AI for some. So these are the two statements of the prime avoidance lemma. We use the second one in this proof. Okay, so this is the statement of prime avoidance lemma. With this, we can stop here, I guess. Yeah, it is time.
Sir, can you just recapture the today's session? I joined much late. So just recapture the today's session. No? I joined much late today.
Okay, so you can, I guess it's better that you can see the recorded session.
I will see, sir. Just 1 minute you give and.
Okay, so we did fifth assignment, second exercise today. So this is the first question. Suppose R is a PID. We have to show that is this R mod I is a PID. Suppose I is any ideal, then for other condition that if I is a prime ideal, then what you can say. But we proved that for ideal it is not true. But if I is a prime ideal, then we prove that this is true. That R mod I is also PID. If then the question asked about the ascending chain conditions in PID, and we prove this is true. Then about descending chain condition, we prove that this is not true. Similar, there are some other questions. You can see the on notes also, right? So I hope it is fine. Anything else?
So just give me another 1 minute. Just complete it now from UFD.
Okay. So So what is UFD? So R being integral domain, then it is a factorization domain. Then if every element can be written as a finite product of irreducibles, right? Here I write the definition. Then it is UFD if the factorization is unique. Like if these have two factorization P1, P2, Pn and Q1, Q2, Qn, then M should be same as N and Pi should be associated to Qj for some J. Now we give some example of factorization domain which is not unique factorization domain, and integral domain which are not unique, which are not factorization domain, which you can see here. After this, we prove this one that I is a prime ideal of R, then R mod I is a UFD. This is false statement because we use the prime ideal x generated by x square plus 5 in ZX and prove that this ring is isomorphic to Z root minus 5, and we know this is not UFD. So by that argument, we are done. So then any ascending chain of prime ideals in stabilizes in UFD, we prove this one fact, and now this is the find, right? You joined from here, right?
Yes, sir. Thank you, sir.
Okay. So with this, I stop here. If you have any comment or suggestion, you can tell me.